How are we? How are you, my dear listeners and students, plus you out there? So in this tutorial I'm going to talk about minterms, maxterms, and then the canonical forms of functions. Let's say you have a function f of n, which is equal to maybe x then plus y. This function always have what we call its minterms, it has its maxterms, and then it can be expressed in terms of canonical forms. So we are going to look into details of these things today as we go on. Alright, so let's look at definitions. How can we define? So minterms is a product term in which all variables appear exactly once, either complemented or uncomplemented. In a table, in a truth table, we have those terms. We can express all values because we looked at a truth table somewhere. So the combination of the outcome is 1 in all the possibilities. So this minterm it represents exactly one combination. Okay, one combination. That means if I have maybe here these rows, and you find maybe this is x and this is y. So if this is 1 and this is 0, this is a 0, and then this is a 1. Wow, this is a 1 and this is a 1. So the canonical form takes only one option in the table. All right, it takes only one option, and then it is going to be denoted by mj. A j will mean the number at which this the number corresponding to the position of the sum in the truth table. So we are going to look at this. Then a max term is an opposite of a min term. This is a sum term. Okay, in min terms, this is a product term, and in the max term, this is a sum term. Please note that. So it's a sum term. Variable appear exactly once, either complemented or uncomplemented, and we shall be using mj to denote a max term. All right, so let's look at the example. For example, we have this truth table of 2. So for x, y, and z, we all know how to name this. So we have x, we have y, and z. So I want us to follow very well such that we understand this, even on the theoretical part. So can we get all possible values of z, x, y, and then z? In class we discussed about this technique of getting all these. I think let me use the easiest. We said here we use 2. No, we don't use 2. I think so we use something like this is 1 powers of 2, and then this is 2, and then this is 4. Okay, so let's write you write a 1 0, a 1 0 1 0 1 0 1. All right, let's go back here. You write 2 2. What is here? So we write 0 0 1 1 0 0 1 1. Okay. Then here you write 4 4 0 0 0 0. All right. 1 1 1 1. So I hope everybody now can guess, can understand how we got that part. Okay, now let's go to the min term. In the min term, is just exactly write what is here, but using the x, y, and z. So we say that wherever x is equal to 0, that means we have what? We have not x, okay? And then where x is equal to 1, that means we have x, okay? So this is a negation. Where there is x 0 y 0, it is a not x, and then where there is x is 1, this is an x. All right, so you can write it as this, you put a bar, or you can write it as this, you put a complement here. Okay, so the same thing. So this and this, they are the same, they all mean not x. Okay, yeah, they all mean not x. All right, so, and we looked at the not get. I think somewhere we said the not get is something like this, if I'm not mistaken. Maybe here we have an x, yeah, we have an x here, and then the outcome is going to be x naught. All right, so let us see how we are going to do this. Where there is a 0, you put not x, okay? And remember that min term is a what? Is a sum of products. All right, is a sum of products. So it means you have to multiply these ones, and if you're going down, you are going to add. So this is the difference between the min term and the max term. The min term is a product, and then the max term is a sum. Okay, yeah, so let's now see. So we have a 0 here, that means we have a not x. We have another 0 here, that is a not y, and then we have another 0 here, which is a not z. So, and this is going to be m naught. So I think 0 is now our j. Okay, is now our j, because min term is not denoted by small m, j. Okay, so the j is 0, so the position of j varies from 0 up to 7 for 3 variables. That's for 3. If there are 4, maybe it would increase. Okay, so let's go on. We have a 0, which is not x. We have a 0 of y, that is a not y. And then we have a 1 of z, and that is why here we have a z, okay, which has no not, and that is our m1. Again, we have a not x, which is not x, and then we have a y, which is a 1 not complement, and then a z, which is that z is 0. So you can continue with that technique downwards. You get all these m's up to down there. So I hope we are now well conversant of how to get the min terms of this of the three variables. All right, now let's go to maxterms. Maxterms is a product of sums, so these are the sums. Okay, yeah, these are the sums, and then the maxterm is denoted by capital M, then J, whereby J will represent the position of this term in a given table. Okay, all right, so let's look at how to get it. So where there is x, where there is a 0, that is a not x or not y or not z, and then where there is a 1, we shall put a 1. So, but we know that a max term is an opposite of a min term. So if here where there is a 0 I write not x, then in a max term I will write an x. All right, yeah, you convert. Actually this is a conversion because you're looking at this product 1, you get it. All right, so sorry for that, let's go on. So this one is an opposite of this. So let's now look at how to get this. So if we have x as a 0, that means it is a not x in the min term, and then here it is an x. How can we make this one 1? Okay, by just removing the complement. So if the min term is x, so that means the max term is going to be x complement. Okay, and if the min term, actually vice versa, okay, it's going to be vice versa, which is an opposite. So if this is a 0, we shall have a y here, because here we have a y not, and then this is a 0, still we shall have this. So this is the capital M not. If we continue with the same trick, so where there is a 0 I put x, and then where there is a 0 I put y, and then I see here there is a 1. To make it an opposite of this, I have to complement it here. Okay, all right, so let me do one more. If you have a 0 here, here we have an x complement, so to be an opposite of this, or to be 1, I'm having this x, and then to be 1, here I have something that is not complement, so here I have to complement it, make it an opposite of this, and lastly z, which is 0. In min term I have z complement, but here I have not to complement it, so I have m2 of this thing. So continue with the same thing up to down. I think you'll be able to get all those things down there. All right, so let's look at conical forms. Each function, for example f of x, right, so for example f of x maybe is equal to a plus, I'm going to give it a plus b, so it can be expressed in canonical sum of products or canonical product of sums, and basically this is what they mean. That function can be a sum of all these here, a sum of all those. You can say fx is equal to this times that times that, or you can add these ones. Okay, all these ones, so you derive all these ones and then you add them. Let's say this was a and this was b and this was b, so I can get its canonical form from here. this, we know the table. Let me draw here some small table, and we have we have here. So what I'm going to have here, let's say we have A, and then we have here B. So we have A plus B around here. So we have A plus B there, because remember our function, which is f of n, is equivalent to A plus what? Plus B. All right. So here I'm going to write beginning with 0, 1, and then 0, 1. Then here 1, begin with 0, 0, 1, 1. Okay. So A plus B, this is O, not so. This is an O operation because it is a plus. So this or that, I think here I get a 0. This or this, I get a 1. This or this, I get a 1. And then this or this, I get a 1. Okay. So from here, if I want to make remove this. And then if we continue and we want to make something like a product of sums, let's say. So I'm going to put here another thing, and I put small m. So this is min term. So small m j. Small m of j, I think m1 is going to be all right, let me extend this line. Extend this line somewhere. So the min term is going to be this is A, all right, times what? Times a here A naught, and then this is B naught, not B. Okay, that's it. Now here we have, if this is A plus B, that means the final answer here I'm going to have what do I have here? This is A plus B. This is 0, which is A naught. Okay, and then this is B. Then what about here? This is A naught. This is A naught. No. That is A just. And then this is B naught. This is B naught. And then lastly, this is A naught times B naught. So this is the sum. What I have here now is the min terms. So I can express this f of n in terms of its min terms, and that is going to be canonical sum of what? Of products. I'm adding products, sum of products. So these are products. So I'll look for where this thing is 1. Okay, that is where I'll have to add only. So this other 0, no, I don't add it. So that is equal to A bar times B alone. And then I add another product, which is this A times B naught. Okay, and then I add another term, which is A bar times B. Okay, so this thing here now is our fn in terms of min terms. So in min terms, you check where there is 1. If you didn't get it very well, we are going to look at it in details just today, don't worry. So same applies to conical product of sums. So let's look at the example here. You get it more deeply. So we have a function, we are saying given the truth table below, this describing a function f of n in terms of a, b, and c, then express it in canonical sum of products and then canonical product of sums. All right. So we have a here, we have b here, and we have c. Can we get all possible values of this? All possible values of this are 0, 1, 0, 1, using the other technique of 1, 2, and then 4. So you can be able to get all these values here up to here, okay, up to there. So this is what they said, that for a given function, it varies, this f, it varies with a and b, c, this one. So they maybe got an answer or a product somewhere, and then they put it for us here. So they want us to get the canonical sum of products. So remember, canonical sum of products, in short, this is min terms. Okay, this is min terms. So they want us to express it in terms of min terms, and then terms of canonical product of sums, that is max terms. Okay, so let's go on and answer number 1. So solution for A, canonical sum of products. So you know that in min terms, where there is a 0, you put that value, which is a naught. So let's first get it, and remember that in canonical sum of products, around here, canonical sum of products, they are saying that the min terms included are those mj such that f of this is equal to 1. Okay, f or the function is equal to 1. So let's go and see where this f is equal to 1. Where do we get f is equal to 1? Around here. This is in this row, in this row, and in this row, lastly in this row. So this is what we are going to do. We are going to look for where this f is 1, which is here. Sorry, this is not 1. We want where this thing is 1, where it is 1. So we have this row, I think that is where it is 1. Then we have another row here, which is 1, and we have another row here where this is 1, and then another row here where this is 1. If you're wondering how I'm getting them, I'm considering f1 where the product is 1. Okay, where the product is 1, where the product is 1. Alright, so if we are to add it, we shall say f, our f of something there is equivalent to, let's begin with the first row. The first row is this. So we have a as a 0, it becomes an a naught. Okay, times we have this one as a 0, so it becomes a b naught, and then this one as 1, which becomes a c. So but remember that canonical sum of products, it means that you add the products. Okay, so I'm going to put a bracket here, and then I put an addition here to add another product. Okay, this is a product, and then this is their sum. All right, so when I add here, erase this thing here, I remove this and then remove that, such that we continue very well. All right, so we add another one here. This is a 0, which is a, that is a naught, and then times this is 1, so this is b only, it is not complemented, times this is a 0, and that is a c complement. Okay, so plus, guys, plus what? We have another row here which is a 1, and that is a only, not complemented, times b, which is a 0, so it is complemented, and then times 0, which is a c complemented. Okay, are they over? I don't think so, because we are from here. So lastly, this a 1 in a means a just, and then a 1 in b, it means a b not complemented, and then a c here which is complemented, that one becomes a c. So therefore here we have expressed this function here as the sum of products. So these are products here, these are products here, and then we are adding them. Okay, we are adding the products. So that is all about expressing a function in terms of sum of products. All right, so let's go to another question, which is solution B. We want to present this in terms of canonical product of sums. Okay, product of sums, or POS. Sometimes they call it POS, which is POS. Okay, product of sums. Now we look for where this F1 is 0. According to this definition here in product of maxterms, actual and product of sums, we look for where this thing is 0. Okay, so let's go down and then look for where this thing is 0. So we have this column, that is where it is 0, and then we have this column here where it is 0. We have also this column here, is it a column or it is a row? And then lastly we have this. Have I jumped anything? I don't know. I've included this, included that, I've included that, and that. Okay, so our Fn, actually they don't have an n inside, so you can just remove this n inside. Yeah, it was just anything. Oh, sorry for that. We have 0, 0, 0, 0, and then we have this. So max term, we say this is an opposite of a min term. So where there is a 0, for us we put a 1. Where there is 1, we put a 0. So in 0a here in max terms is going to mean an a, and then plus this one here is going to mean a b, and then here plus a c. Okay, and if you are wondering how I'm getting as a b c, why am I not complementing them since they are 0, we said that max term from here above, we said that max term is an opposite of a min term. If this is a complement and then here you don't put complement in max terms. All right, so that's why I'm getting them. So times, remember that here we have product of sums. So this is a sum and then we are multiplying it, so it becomes a product of sums. Okay, so times, where there is a 0 which is here, I take an opposite. So that is, if this is 0, that means it is an A, plus if this is a 1, that means I have complement B, yes, and then plus 1, which means I have a complement C. All right, are they over? No, we have another 0 here, so plus 1, that means complement A, 1, that means complement A, plus we have a 0, that means B, which is not complement, and then have a 1, which means complement C, which means complement C. So times, okay, it's the times, okay, it's the times, excuse me, and then times this one, which is last, a 1, that means I have a complement A, where there is 1, and then plus I have a 1, that means a complement B, then plus another 1, which means I have complement C. Yeah, so they are done. All right, so by doing this means you have what we call a product of sums, okay, product of sums, and this is what we logically mean, that these are sums and then you multiply them. Okay, these are sums, you multiply them. These are sums, multiply them. So that is it. In most cases this thing is called POS, product of sums. Same applies to this. Sometimes it is called SOP, and that is sum of products. So here you're going to multiply what we call min terms. Okay, multiply what we call min terms. Okay, so down here you have you multiply the max terms, the addition of max terms. All right, thank you very much. Let's meet in another session.